Our speaker today is Antonio Rieser, and he will be telling us about algebraic topology of mesoscopic spaces. Take it away.
Okay, well, thanks very much for the invitation. This is a fantastic forum, so it's really nice to be able to be here and to speak. So I'm going to talk today about a series of things around which I've been thinking about for the last couple of years. And it's how to do algebraic topology on a metric space decorated with a specific scale. And so the beginnings of this problem start with a picture kind of like this. I'd like to know, so when I first got into algebraic topology, I was into applied topology, I was very interested in this problem, and I never stopped being interested in this problem. So if I have some normal topological space, like a CW complex or something, and you suppose we have some metric on it and maybe even a measure, and we take a sufficiently dense subset but finite, when can we say, not that they're close like persistent homology, but is there some way to say that they're actually equivalent, in a reasonable sense? And what I'm really looking for are maps back and forth, right? So, and the map this way is simple enough, right? It's just the inclusion, right? But the map this way is not at all obvious. There's a kind of cousin problem, which turns out to have the same solution. So as I was, rummaging through the literature, you find here and there that people like to set up the problem or like to set up persistent homology or Vietoris-Rips complexes or something in metric spaces, the category of metric spaces, and one Lipschitz maps. And for me, this is problematic because although it gives you it makes the constructions functorial, most of the interesting about half of the interesting maps are not actually in the category. And so if one of the things I want to do with my functors is take an expression like this, so I have a bijection or something, and then hit it with the functor and conclude that the functor is applied to that map is also an isomorphism. And you can't do that here. So we're gonna talk about that as well. I mean, the same thing works. All right. So the issue in the last case is that if my functor is assigned a scale, it's very difficult to change the scale to compare to different scales. It's not impossible, but you end up moving to natural transformations or something. This is there's a lot of bookkeeping involved, so we'd like to try to avoid that. And the idea is subtle but very simple, which is to move the scale from the functor into the space. Right? So instead of having an infinite number of functors applied to a metric space, I'm going to have an infinite number of spaces, my metric space decorated with a different scale, and then a single functor. And this way, I kind of avoid this issue of not being able to compare scales, as long as we set the maps up right. So now we have to figure out what the maps will be. So we know kind of what our space should look like, and our morphisms should be maps that respect not the metric so much, but really the scale somehow. And so we're going to make that precise. So our maps now, this just looks like or just is a variation on the standard epsilon delta notion of continuity. So if f is a function, I left out the metric space, but okay, they're metric spaces. And then for every epsilon, for every x, there exists a delta depending on x and epsilon greater than 0, such that the distance of the in the domain is less than, instead of just delta, now I have a scale, implies that the distance in the range is less than a scale plus epsilon. Right? And so I'm going to call this PQ continuous, just indicating the different scales. When delta is independent of x, which will show up later, we call it uniformly PQ continuous. Okay, so similar notions actually appear in the literature, particularly in this work by Konrad Plaut and his collaborators. So they study a variation of this, really focusing on uniformity. When P, depending on exactly what the domain is, they're really looking at the fundamental group at different scales in the range. And so they're going from either some, what I think of as a graph, some string of points to the range, where the distance between the points has to be less than a certain distance in the range. Or sometimes they want to go from the circle. So in that case, P is 0, the topological circle, right? But in any case, in both situations, their delta doesn't depend on X. Okay, so now, first thing we observe is that we get maps like the ones I wanted to get. So you can go from something like the circle to, 4 points, given appropriate choices of P and Q. So in here, P can be 0 and Q can be whatever the distance between neighboring points is. And you end up with a this continuous map, but in this new sense, where you allow kind of controlled discontinuity. Okay, so we're going to now give these names. So MES, I'm going to call it metric spaces with a distinguished scale, or mesoscopic space, and PQ continuous maps, and UMES is the mesoscopic spaces, and uniformly PQ continuous maps. So now, however, since I'm a topologist, I don't just want to study those categories, but also relate them to topological spaces or uniform spaces. And so I'm looking for categories that have a minimum of all of these things. And I should add here and maps, spaces of maps between them. I'm going to say, yeah, as full subcategory. Actually going quite fast. I might end up being short. Okay, so for better or worse, if you go through the literature, particularly both the early literature on point-set topology, but also there was an explosion of consideration of different categories in the 70s and 80s, a little bit in the 90s. You'll find, all of these different possibilities that contain at least topological spaces and or uniform spaces, and you can get them to contain also mesoscopic spaces or scaled metric spaces. And I've indicated, so here's a sampling. I've indicated with red at least what contains these three. So not all of them contain the spaces of maps, but these objects that we want to look at. All of these are options for that. So we're going to start conservatively and go to the next most complicated one in both situations, and then see if we really need to go much farther out. And it turns out you do need to go a little bit farther out, not much. At least if this is these are your desired objects of study. Okay, and we're going to inspire ourselves by the relationship between metric spaces and topological spaces, and metric spaces and uniform spaces. And our choices are going to be very deeply informed by this. So here we have in the top over here, we have metric spaces and uniform continuous maps. These fit into uniform spaces. Metric spaces with continuous maps, of course, are topological spaces. There's a functor from uniform spaces to topological spaces, but it's neither injective nor surjective, it's just a functor. And then over here, we have this big mess of stuff. So here we have reflexive undirected graphs. They can sit inside uniform mesoscopic spaces if you play with P and Q, right? These guys sit inside what are called semi-uniform spaces that we'll see in a second. Reflexive directed graphs, we can put inside closure spaces, mesoscopic spaces as well. And the spaces of functions make things more complicated. So if we want them to be nice, well, we have to go a little bit more general and talk about pseudotopological spaces. I'm not going to talk too much about those other than that they exist and it's sort of nicer to work there. It's much, much easier to describe closure spaces and semi-uniform spaces. Most of the main ideas already appear there, but just so you know, this does exist, and in the future, it'll probably be where most of my work will go. Okay, so here are our choices, and we've, oops, this is the wrong version. Anyway, so semi-uniform spaces here are well adapted for Vietoris-Rips cohomology. Cech closure spaces are well adapted for Cech cohomology. Should be well adapted for Sheik theory as well. I'm going to defer that a little bit because I was planning to do it, but I realized I actually have too many options and I don't know which one's the best one or which ones are silly. So that'll be for my next talk. And then pseudotopological spaces are very good for homotopy theory. So we'll describe each one. Okay, so let's start with some definitions. This may or may not be familiar. A filter on a set is just a bunch of subsets of the set such that it's closed under supersets and it's closed under finite intersections. And the empty set is not in the collection, right? So not an element of the collection. And so what this means in particular, if we combine these two things, is that if I have two elements of my filter, the intersection has to be non-empty. And the classical example, the typical example that you should keep in mind, are the open neighborhoods of a point in a topological space. So a semi-uniform space now is going to be a pair where we have some set and then, some structure on it. So the structure we're going to put on it is a filter on the product, and here the Cartesian product of the sets, such that for every element in the filter, the diagonal is a subset, and also for every element of the filter, the inverse. The inverse is in the filter. So this gives it a certain kind of symmetry. And a semi-uniform space is a generalization of a uniform space, and it becomes a uniform space if we also add an additional axiom, which is this. It's kind of funny looking, but it says that if you have an element of your filter, there exists another element such that its set product is also in the filter. Oops, what's that? No, I'm missing something. So the set product is inside you. Okay. Okay, and then uniform continuity, we basically borrow from uniform spaces. So a function is uniformly continuous between semi-uniform spaces if and only if for every element in the filter in the range, there's an element in the filter in the domain such that f of u sits inside V. Okay. And why do I want this? That's why. Okay, so a little bit of terminology very quickly. We have a metric. We have these four properties, and there are a whole bunch of prefixes that one will see if you wade into this literature. Pseudo is going to mean we kill the fact that the metric only is 0 if x is equal to y, so it can be 0 on different points. Quasi, we kill symmetry, and with semi, we kill the triangle inequality. So you can then play with these different combinations of prefixes and get different kinds of structures. And so the one that's going to interest us is this one here, semi-pseudometric. So that is something where this is 0 on the diagonal and is symmetric, but it can be 0 elsewhere, and also doesn't necessarily satisfy the triangle inequality. Okay, so we're going to build a semi-uniform structure from our semi-pseudometric. And so how do you do that? So you take your semi-pseudometric, and then I'm going to look at all of these sets such that for every possible r greater than 0, I have the sets of points or sets of pairs where the distance is less than r, right? So now I have this whole collection of sets, and that's going to generate my filter. I put a D there, indicating it comes from D. And generating just means the following thing. So if U is in the filter, if and only if there's some R greater than 0, such that U sub R is contained in U. Okay, and so you can show, it's not too hard, that this is a semi-uniform space. If D is a pseudometric instead of a semi-pseudometric, then you can show that, here, XFD is a semi-uniform space. If D is a pseudometric, then you can show that you get a uniform space. And so this is more classical. Okay, so I wanted to talk about mesoscopic spaces. So then I have a metric and a scale. And I'm going to take those two pieces of data and construct a semi-pseudometric out of them, right? So this is also fairly, not completely elementary. So we have our metric, we have the scale, p greater than or equal to 0, and we just take the max of 0 and the distance between 2 points minus p. So I just, stomp on anything that has a distance of minus p, or a distance of less than p. And this is a semi-pseudometric, and it becomes a pseudometric when, or even a metric, when when p is equal to 0. So if I start with a metric, I get back a metric, start with a pseudometric, and just get back the same thing. All right, so obviously combining those things, we get a semi-uniform space given a metric and a scale. So first I construct my semi-pseudometric, and then you construct the semi-uniform space given the scale, given the semi-pseudometric. All right, we're going to call this Q. Okay, some nice examples. Oh wait, did I? Yeah, okay, here's another example. You can also do this with graphs. So if I have a graph, E is already a subset of V cross V. So if I take my space to be just the vertices, I take my filter to be the filter in the V cross V, or X cross X now, generated by the single set, then this also gives me some uniform space. And the first indication that we're doing something right here is that uniform continuity in the semi-uniform sense is identical to uniform PQ continuity. So this is just a little theorem. So if we have two metric spaces, F is uniformly PQ continuous, if and only if it's uniformly continuous as a map between semi-uniform spaces. You have a similar notion for graphs. So if I have a reflexive graph homomorphism, so that is, I get two vertices connected by an edge, either go to two vertices connected by an edge or to the same point, or to the same vertex, then also you get, that's uniformly continuous in the semi-uniform sense, in the induced semi-uniform space. So with graphs and these mesoscopic spaces, it works very nicely. Okay, so the first thing I'm going to try to do with this is generalize a construction of Hausmann. So he has this metric homology, which is constructed in the following way. So if I have a pseudometric space now, not semi-pseudometric, but pseudometric, and some subspace, then I can construct some cohomology by taking the limit of the Vietoris-Rips complexes, or the relative cohomologies to these Vietoris-Rips complexes at scale epsilon, and I look at the limit as the direct limit as epsilon goes to 0. And then Hausmann shows that this functor satisfies some versions of the Eilenberg-Steenrod axioms adapted to pseudometric spaces and uniformly continuous maps. So that means that, homotopy is going to be a uniformly continuous map. And there's a funny kind of version of the excision axiom. But there's a peculiarity here, which is in Vietoris-Rips complexes, we'd like to stay away from zero, if at all. I mean, we'd like to have the option anyway, of staying away from zero. But Hausmann's construction, or Hausmann's theorem rather, is false if epsilon stops before it gets to zero. And so excision looks like this. XY is a pair, and U is inside Y, such that the distance of U and the distance of the complement of Y is greater than zero. And then we have this homomorphism induced by inclusion. And it's an isomorphism. Sorry. So that's what excision looks like for Hausmann. So now the idea is that instead of, note that here we start with a pseudometric space. So instead of that, we replace that with semi-uniform space, and in particular semi-pseudometric. We should hope that you can relax this condition to epsilon going to P. Okay, so how do we construct Vietoris-Rips cohomology for semi-uniform spaces? Well, remember that each element of F is some subset of X cross X. So we can think of this as a graph, right? In fact, you can quite literally think of it as a graph. You take the click complex of that graph, and then you check that you end up with a directed system because you have these graphs are constructed from a filter, and you take the direct limit of this directed system. So we decide that, or we define the Vietoris-Rips homology of our semi-uniform space as the limit of the homology of these click complexes, where the click complexes are generated by the graphs given by the elements of the structure. And similar thing for pairs of spaces. The pairs kind of fit together nicely, so you can do that well. Okay. So the first thing we'd like to see with this more general construction is that it reduces to what we understand in specific cases. So for a graph, semi-uniform Vietoris-Rips homology is exactly the click complex of the graph. So why is that? Well, it's exactly because in this limit, I have a maximal element, which is sort of the smallest graph in my filter, which is just the original graph. And so this limit ends up just being the cohomology of the click complex, and that's the Vietoris-Rips cohomology. So that's very nice. Similarly, it's not too hard to see that the Vietoris-Rips cohomology, the semi-uniform Vietoris-Rips cohomology for a mesoscopic space is exactly this generalization that we wanted to get of Hausmann's results. So the direct limit of these cohomologies of the Vietoris-Rips complex at a scale as epsilon goes to some fixed scale, possibly non-zero. And our first result. So first, how does homotopy work? It works kind of like you would expect. Since normal metric spaces are also semi-uniform spaces, the interval is there. There's a way to define products. So homotopy is just, really exactly the same definition as you get in the usual case. I have two functions are homotopic if and only if there exists some uniformly continuous map on now X cross the normal topological interval to Y with the standard conditions. Okay, and we have a corresponding corresponding theorem to Hausmann's theorem. So this semi-uniform Vietoris-Rips complex, or cohomology, satisfies Heisenberg-Steenrod axioms, this time for semi-uniform spaces and uniformly continuous maps, and with a kind of modified version of the excision axiom, which is adapted to semi-uniform spaces instead of to pseudometric spaces. And this is what excision looks like. I realized as I was writing this, it can be simplified a little bit, but okay, this is what's written. So if F is a semi-uniform space, and we have this triple BAX, then suppose we have an element in the structure such that for every U that's smaller than it, or U that's contained in it, including that element, then this set, which is all of the elements of U which are related to B, or related to some element of B. And note that since the diagonal is contained in every set of the structure, that includes B. So long as all of the elements of U that are related to B are inside A, then we get this isomorphism, the excision isomorphism. And if you kind of unwrap this and interpret it in terms of pseudometrics, you get exactly Hausmann's condition. Where did it go? Exactly this. Okay. An example of a acute application, very simple. I imagine maybe this appears somewhere else as well, but this is like 3 lines with this little bit of technology. So if I have concentric circles and nothing between the concentric circles, the space between them, I'm going to say, is always epsilon. Then it happens that, so my maps allow little jumps, right? And the homotopies in particular allow little jumps. And so I have a homotopy equivalence from the innermost circle to this whole set of concentric circles. And so that goes like this. The set of concentric circles goes to the innermost circle just by sending everything to the innermost one, which goes back to the set of concentric circles. And we have this homotopy with little jumps, so that, yes, which gives us homotopy equivalence to the identity, or a homotopic map to the identity. And then backwards, it's even simpler. And so this is exactly the identity, right? And so in this case, we now have homotopy equivalence between these 2 sets, but only for certain scales, not all the time. So if my, should be F. So only if my semi-uniform structure, the mesoscopic space, has a scale that's big enough to allow these little jumps to happen in the homotopy. And in that case, we have this isomorphism between the Vietoris-Rips homologies of the innermost circle and the Vietoris-Rips homology of the whole collection of concentric circles. Okay, so that's what we're going to say about semi-uniform spaces. Now, the kind of cousin structure, which has very much the same relationship to semi-uniform spaces as topological spaces due to uniform spaces, are called Cech closure spaces. And the structure here, we're going to define it, instead of like via something like open sets, we're going to define it through a closure operator. So here we have some closure, which takes a set and gives you back another set. And it has to satisfy these 3 axioms. So the closure of the empty set is the empty set, closure is expansive, so it contains its argument. And the union of the closure of the union of 2 sets is the union of the closures. Now, if I also include an extra condition so that it's idempotent, then C induces a topology just by taking the open sets to be the complements of all of the closures of every other set. And this gives you, in fact, every topology you want. A continuous function is defined in the following way. So F between 2 closure sets is continuous if and only if F of the closure of a set for every set is contained in the closure of F of the set. And just like in semi-uniform spaces, we have this this condition looking at not uniformly PQ continuous, but now just regular PQ continuity. So a function between two metric spaces is PQ continuous if and only if it's continuous as a map between, but I didn't define these yet. So between two special closure spaces, which I'll define in a second. Let me define these first. So the special closure spaces are the following. So if I have a metric space and some scale greater than or equal to 0, then for any subset, I take the closure of that subset to be all of the points within a distance p of the subset. And when scale is 0, I get back the usual metric topology in a topological space, right? So this PQ continuity is equivalent to continuity in closure spaces with those two structures. And you can also do this with graphs. Now, unlike in semi-uniform spaces, I can have non-asymmetric structures. So I can include directed graphs as well as graphs. And this is an extremely simple structure. So if I have a graph, take a vertex of the graph, the closure of a vertex is going to be the union of the vertex itself plus everything that's connected to the vertex by an edge. And then for an arbitrary subset, I just take the union of all of the closures of the elements of the subset. And so that's a closure space. I did this. Okay, so closure spaces, I think I said, yes, I didn't emphasize this, but the thing to remember about them is the following. They're entirely determined by neighborhoods of every point. So if you have some set, and say you have some collection of sets at every point that you want to declare are the neighborhoods. Now, maybe they don't satisfy the axioms for topology, but they're sort of pretty good, and you just want to declare them to be the neighborhoods. For instance, in a point cloud, you might want to declare that every neighborhood has to contain a ball of a minimal size. So that's exactly these mesoscopic spaces. And this gives you a closure space. Right? So closure spaces are absolutely determined by deciding what the neighborhoods of every point are. And we see how to do that first by figuring out what the neighborhood means. So the interior of a set in a closure space is going to be the complement of the closure of the complement. It's an unfortunate definition, but if you think about it for a moment, it's also true for open sets. Just open sets is also the whole set. And so use a neighborhood of a set A if A is in the interior. Right. So now, so what can happen here? Because my closure is expansive, suppose I have A, and suppose my closure sort of expands sets a little bit. So I look at the complement of A, then I look at the closure, so that's going to expand the complement a bit and collapse A into something smaller. And then I look at the complement of that, and so I get this bit here that's left. So that's going to be the interior of A in a closure space that's not topological. Okay. And then the natural notion of covers for closure spaces is an interior cover, and the interior cover is this. So if I have a cover, it has to be a normal cover, but it also has the property that X is the union of the interior of all the sets in the cover. Okay, so neighborhoods are very important. Here is the theorem that says that neighborhoods are equivalent to constructing a closure space. So if I have for every X, I have some collection of sets such that X is in every one of the collection, every element of the collection is non-empty, and I have this condition about the intersections. Then there's a unique closure structure such that these collections generate a neighborhood filter at every point. And in particular, the closure looks really just like the closure operator in topological spaces. So it's all of the X in your set such that for every possible neighborhood, the intersection of the neighborhood with the set is non-empty. Okay. You can also get closure spaces from semi-uniform spaces in the same way. So instead of, I'm going to now define my neighborhood base rather, by all of the elements of, so every element, every set of a neighborhood base is going to be set some collection that is related to X in an element of the semi-uniform structure. And so this gives me a closure space. And also every closure structure that's symmetric in this way comes from a semi-uniform structure. Maybe you don't know which one, but it's at least there. So closure spaces are the range of some functor between semi-uniform spaces and closure spaces. And what this says is that the image of the functor are exactly the closure spaces with this imaging property. It could be that you have more than one, in fact, it's often the case, more than one semi-uniform structure that gives you the same closure structure. Okay, so I wanted to do, I think this is a good moment to mention that Cech cohomology just works. It's maybe modulo excision. I'll put a question there. So this is a student of mine. Cech homology with interior covers. And by just works, I mean it's homotopy invariant. You have some version of excision, although what he proved is a little bit weaker than one would ideally like. So this is Palacios a couple of years ago. It's also implied by older work by a guy named Bentley, but he didn't talk directly about closure spaces. He talked about what are called mesotopic spaces. But his version actually implies with a good excision condition. So, you know, it should also be fine. Here too, we just have to find the argument. And, you know, so what you prove is that actually every closure space induces some mesotopic space and then applies there. Okay. So homotopy is not great in closure spaces, although it's possible to define homotopy groups and so on, for the following reason, that closure spaces aren't Cartesian closed, which makes dealing with function spaces difficult. So path spaces, loop spaces, all of these things, they don't have a canonical closure structure so that the evaluation map is continuous. And you really, really need this if you're going to do any kind of more sophisticated algebraic topology. But if we take kind of the next best thing, which are pseudotopological spaces, it does have this property, right? And so a pseudotopological structure is something else. It's defined via filters as well, but this time on the original space, not on the product. But suffice to say that it's Cartesian closed. And in some recent paper, I showed that there's a model category structure on pseudotopological spaces, which looks very much like the model category structure on normal topological spaces, where weak equivalences are weak homotopy equivalences, fibrations are Serre fibrations, cofibrations are retractive relative cell complexes. So I went from something completely elementary to something that, you know, at least as far as the words go, are not so elementary. But suffice to say, what this is saying is that pseudotopological spaces are a very good place to do homotopy theory. And so the basic results we expect from reasonable homotopy theory are there, at least with these certain choices. Some examples of our homotopy groups. So the one thing that I know how to compute is pi1 of the circle with different closure. Oops, this is not X, this is S1, with different structures. And homotopy is exactly what you expect it to be. So pi1 of S with a closure structure, or say pseudotopological structure, because they one induces the other, is what you expect when P is sufficiently small. Here, sufficient is less than a third, and is large, and is trivial when P is big enough so that the whole space collapses. There's also an isomorphism of fundamental groups that's given by a function, right? So this was going back all the way to my first slide, right? So this was kind of what I had hoped to find, is some sense of equivalence. Here, I'm a little bit shy of complete equivalence, but we have probably the most important step, which is that we have a function from the circle to here Cn is some cycle, and then the little Cm indicates how many neighbors every point has. So if n and m are balanced appropriately, then this map between fundamental groups is an isomorphism. Okay. So I want to end with quickly reviewing some work that I like very much by Nikola Milicevic and Peter Bubenik, who's in Nikola's thesis. So he noted. So I've all of my work has been with using the topological interval, doing very strict generalizations of algebraic topology. What they noticed was that when you leave topological spaces, you actually have a choice of both intervals and products. And each combination of those choices gives you a different definition of homotopy and a perfectly good and different homotopy theory. And so the products that they looked at were the standard categorical product, where your kind of basic neighborhoods are squares of neighborhoods in the factors, and then what's called the inductive product, where your basic neighborhoods are crosses of neighborhoods in the factors. This looks a little strange, but in graphs there's a good interpretation. And then we have three possible kinds of intervals. One is just the topological interval, which is what I've been working with. One are all possible intervals. Like if you were to replace the interval with a graph, this is what you would get. So it's all possible, like graphs and vertices where the neighbors are connected. And then a directed version of that where the neighbors can be connected with edges going one way or the other, and the direction doesn't really matter. And for each one of these choices, you get a different notion of homotopy and different homotopy theory, right? So that's what I'm saying here. And furthermore, they're related to each other. So there are continuous maps between the intervals, and also there are continuous maps between the different products. And when you put all that together, this creates the following diagram. So this is from Nikola's thesis again, slightly different notation, but. And if you look closely at what each of these things is, you realize that lots of them appear in the literature in different names, generally looking at some kind of homotopy for graphs or homotopy for metric spaces or something else. And so, the inductive product, we're looking at some kind of graph homotopy, which is called A theory, that's been studied for about 20 years, a little over 20 years. There's digital homotopy that kind of lives in part of this one. They really look at homotopy on grids, but still it fits in here. So my references are all very recent, but actually this has a long history. Computer scientists started it maybe even the 80s or something. And it's kind of, there have been moments of activity and then die again, and moments of activity, dying again. But now we're seeing a little bit more activity. There's what I might call metric homotopy, where by Plout and his collaborators, where you're doing something very similar to what I was doing about the mesoscopic spaces. You kind of weaken continuity a little bit, and you send cycles of graphs into your metric space. And then the thing with the classical interval. One which I think is fascinating, which doesn't fit in this picture, is homotopy on non-reflexive graphs. So this time my maps are not allowed to collapse two vertices into a single vertex unless there's a loop. And so this ends up being, from the point of view of homotopy theory, crazy. From the point of view of combinatorics, it's actually very, very natural. And so there are people who have studied notions of homotopy there too. And it's a fascinating thing because nothing acts like you expect. Okay. Other notable constructions in this kind of line of work. So I mentioned Luis, and then some other things that Peter and Nicola did. Actually, they did lots of things, but I'll mention two. So singular homology and cohomology, using, again, different models of simplices depending on exactly what kind of interval you take, and then whether you look at a cube or a simplex or so on. And then they also looked at stability for persistent homology, which has a particularly nice formulation in this context. And so that's it. So let me thank you. Very much.
Great, thank you very much. And let's please all unmute ourselves so that we can clap together for our speaker. And before I will ask everyone for their questions, I saw that there was already one question in the chat. Mm-hmm. I overlooked it, so then I decided to just ask it a bit later because then you were already at a different topic. Mm-hmm. So the question was by David, namely, can the semi-uniform spaces work with hypergraphs where an edge can join as many vertices?
Right, no. So going back into this, where's my... So for hypergraphs, you have to actually go quite far out. So hypergraphs live here. Mm-hmm. And there's certainly some kind of homotopy theory, but it's going to be a little bit strange because when you try to glue intervals, even topological intervals, in this category, there's the point in the middle. It's not isomorphic to the original topological interval. Like the point in the middle actually has a finer structure than all of the other points. And so that makes developing homotopy a little bit more complicated. It's still, I imagine, possible, but I haven't looked at it much beyond identifying a few of the problems. Yeah.
Thank you.
A great question.
Then David has a second question, but I want to first give other people also the chance to ask questions. Who has a question? Yeah, Georg, please.
Hi, Antonio. Very nice talk. Thank you so much. I feel silly asking a question because I'm not an expert at all in almost anything you said. Okay. The way I think about this is from a signal processing perspective and in terms of sampling theory. And the old school way to get to topology there is through locally compact topologies, like locally compact abelian groups and that sort of thing, and then you get a Haar measure, and that's how you get your measure theoretic stuff going. And I wanted to ask if you could help me to connect what you said with that, if there's an easy connection. I don't know. See, I don't even know how to ask the question really.
Yeah. No, I don't think there's an easy connection. Yeah, and in part because it's been a long time since I've looked much at signal processing. I mean, these, what can I say? Yeah, I'm gonna have to punt on that.
That's fine. Just as a comment, like when you define that you're a semi-pseudometric, But that literally is a version of resolution measure, if you think of it experimentally, right? You look at a point, but you only have a resolution by which you can capture that point.
Right.
And so these are very close ideas. So I'm very curious to see if there's a way to connect them, mostly because I need like harmonic analysis. And all of the harmonic analysis literature is in this locally compact language. And so if there's a connection, you suddenly recover all of that. Anyway, so thank you so much. It's super interesting. And I'm going to have to read up on it to understand it better.
Yeah, thanks a lot.
Thank you.
Okay, thanks. Then David has another question, namely on page 34, where you used A, the closure of A. It wasn't clearly defined what A is. Can you elaborate on that?
Sorry, A is just a, so I have a space here. A is just a subspace of the space, subset of the space.
Okay, yeah, I think that should answer the question. Okay, great. Then Peter has a question.
Yeah, great talk, Tony. Thank you.
Thanks.
When you were looking at Vietoris-Rips, you were using cohomology. So Vietoris-Rips cohomology is a reason for looking at cohomology instead of homology?
Mostly exposition, although there is one technical point, which is that, what is it? The exactness axiom fails because of the, the limits. Because you take an inverse limit instead of a direct limit, right? But you still get a sequence of order 2. I mean, it's exactly parallel to what happens in Cech homology versus Cech cohomology in the classical topological case.
Okay, thanks.
Yeah.
I also have a question myself. In the meantime, people can come up with more questions. Namely, it sounds very much like this is all motivated by applications. Could you maybe go into a bit more detail on how one would use this theory in application?
So I use it mainly to prove theorems. Yeah, so I think the closest we have so far approaching applications is probably these results of Peter and Nicola about stability for persistent homology, given different homology theories. And there, you essentially recover, well, I mean, it's the same but different kind of. You get stability theorems and these persistent homologies. So applications are going to be something which come up. I haven't been concentrating too much on the computing things beyond, at least not by computer. So what I hope to do kind of next, or what I hope will work, which is more complicated than what we've done so far, is to try to get better tools in this language for computing, say, Cech homology or Vietoris-Rips cohomology for larger scales, so that we can kind of expand on a lot of the work that, say, Henry Adams and Ziegler and other people have been doing with those kinds of computations. Whether or not that's applied is, I think, probably a question of taste. But
yeah, but I see what you mean.
Yeah.
Thank you very much. Do we have any more questions in the meantime? Okay, then let's maybe end the public part here, and then we can ask more questions. Thank you again.
Thanks.